So good afternoon, and thank you very much for inviting me to this exciting meeting. I really enjoy all the talks so far, and I hope you enjoy this one too. So anyway, I'm switching the topic a little bit to more something that may be of use to many of us who live in cities. Okay, so the title is Impact of Urbanization on Precipitation Associated with Typhoon Landfall. So the motivation of this is that if you look at the Pearl River Delta region, which Hong Kong is over here, and all this region in 2015, a huge area is actually very urbanized, right? So and the question is, how does that impact on the rainfall? So the urbanization ratio actually has increased quite a bit from 1980. The ratio is only about, if you look at this, the build-up area is only about 10 to the, this is the area, so it's only about 1 to, now it's about 5 in 2015. So it has jumped, the ratio has jumped from about 3% all the way to about 20% being in the urban region, the urban ratio. And then the build-up area, of course, has shot up quite a bit from, this is 10 to the 3 kilometers square. So it has jumped up quite a few times. So what we want to do then is to look at the rainfall in the urban area indicated by the yellow, and then look at the rainfall in the other regions in the South China, in the Guangdong province. And these are the two radar sites which I'll come back to later on. So if you look at all the rainfall from both the urban areas indicated in the yellow in the previous slide and the non-urban areas, for the amount of rainfall during tropical cyclone rainfall, which is defined as plus or minus 2 days of landfall time. So you can see both the urban and non-urban areas have increased rainfall. But if you take the difference between the two, you see that there's an increasing trend in terms of the amount of rainfall in the urban areas. Okay, so, and then if you look at the extreme amount, so this is the area, if the red dots indicates that there's a trend that indicates a significant increase in terms of the rainfall amount. So most of the significant increases are within this urban area. So this is observation in the Pearl River Delta area. Now, similarly, in the Yangtze River region, Shanghai is over here. And so if you consider the red area as the urbanized area, so this area is still also very urbanized. And the increase in the urban ratio is also very significant, as you can see in here. And so if you look at the TC rainfall, this is the extreme rainfall, both in terms of the amount, in terms of the frequency and the intensity. You can see that most of the increase, most of the trend, the positive trend, is all in the urban areas. So in other words, both in the Pearl River Delta area and also in the Yangtze River Delta area, it seems that the urban area has an increase in precipitation associated with tropical cyclone landfall. Okay, so to understand a little bit of that, we come back to the Pearl River Delta and look at the tracks, some of the tropical cyclones. So here are 9 tropical cyclones that made landfall in the South China area. So this is Hong Kong, and this area is what we would look at as the urban area in here. So one look at the reflectivity associated with these landfalling typhoons. So if you look at the reflectivity, this is the total reflectivity at 3 km. The white outline indicates the urban areas. So you see that most of the highest reflectivity is in this area. And in fact, if you just look at those that are greater than 20 dBA, you will see that it's also in this area. And most importantly is that when you go to a heavier rainfall, then you will see that you have more of this in here. So it seems to be that both the rain gauge data and also the radar data indicate this may be the case. So what is the reason for that? So we did a modeling study with the WRF, and these are some of the physics that's in the model in here. And so we did two experiments. We ran two experiments. One is what we call the urban experiment, in which this part is called the urban and built-up area. And the no urban is that you just replace this part here with cropland. Okay, so we want to see how different the modeling results would be. So that's the only difference. Now, in terms of the track, there's very little difference for this Typhoon Nida. This is the case study that we did. So the two tracks are very similar. This is left side is the urban, and the right side is no urban, and the blue line is the observation, the best track. So you see that the two tracks are quite similar. So in terms of the track, there seems to be very little difference. And then in terms of the intensity, there's also not much difference in terms of the intensity simulated by the model in both the urban and the non-urban experiments. So the left-hand side is the minimum sea level pressure, and the right-hand side is the maximum 10-meter wind speed. However, if you look at the rainfall, accumulated rainfall for this period from August 1st to August 2nd, so it's about 1 day of rainfall. This is from the CMORPH satellite data. And so you see that you have two maxima. One is on over the urban area and west side of the urban area, and then there's another maximum to the east of the urban area. If you look at the urban simulation, you see that the both maxima are simulated quite well. So this is the on the western side as well as on the eastern side. However, for the non-urban area, no urban experiment, the western side is really absent, and only you can see the one on the eastern side. So therefore, if you took a difference between the two, you see that if you use urban minus non-urban, you see that the most obvious difference is in the western side of the urban area. And so we want to look a little bit more on this side. So we look at the average conditions within this box, this black box in here. So if you look at the hourly precipitation, this is the landfall time. And so what you see here is that before landfall, there's not much difference. However, after landfall, the urban experiment gives you a lot more rainfall. So this is the rainfall on the y-axis. So you can see that from the hourly rainfall, within the black box, you have a lot more rainfall in the urban experiment. So we want to see a bit about the physics of why this is the case. So obviously with the urban, so this is all the urban minus the no urban. So in terms of the surface temperature, you have an increase in the temperature. This is what you expect. The increase in temperature can be as high as almost 4 degrees in here. Then, of course, because of that, you have a much larger sensible heat flux. So you see that the most of the increase in this sensible heat flux is over the urban area. And then similar, and on the other hand, with the latent heat flux, then with the urban area, you have much less latent heat flux. So there's a negative over this area. But if you add these two together, the total heat flux would still be positive because this one here is much larger than that over here. So the net flux is still an increase in the heat flux in the urban experiment. In terms of friction, and of course you have with the urban area, you have a lot much higher roughness, so therefore your friction velocity becomes much larger in here. And because of that, you have a bit of more convergence. You can see the blue in here. You have a stronger convergence in this area in the surface to 850 convergence. And it's because of the heat the sensible heat flux, you have a much higher convective instability in this region in here, right? So therefore, what we think is that the heat flux together with the increase in roughness is what leads to the increase in the rainfall in the urban area. Now, the other factor that we are beginning to look at, but which we have not looked at very carefully, is this thing here. This is done by another group looking at the effect of air pollution on rainfall. And so they simulated the percentage of rainfall amounts for light, moderate, heavy, and extreme rainfall for clean air and polluted air. For some reason, the color didn't come out very well, so this is supposed to be blue. Okay, so if you compare the experiment with clean air versus polluted air, the light and moderate rainfall cases is that you are in clean air, you have more rainfall, percentage of rainfall amount is higher in the clean air compared with the polluted air. However, for the heavy and extreme rainfall, the polluted air will have much higher percentage of rainfall. So in other words, we have talked about the effect of the heat flux and the effect of friction velocity, the increase in the roughness, and I think we have another third factor, which is the effect of air pollution. And this is something that we are working on right now, but we haven't got the definite results yet, so I did not bring the results to you, but you can look forward to some of the papers coming out later on this. Okay, so what I like to do is to just highlight that this is a possible effect of when a tropical cyclone makes landfall or about to make landfall, then there are many factors that can contribute towards the change in the rainfall. So I've mentioned about the increase in roughness, leading to higher friction with low-level convergence, and therefore rising motion, and so then leads to higher, stronger convection and diabatic heating. And then, of course, then if you have moisture coming from the ocean, you can have this increase in the convection. And the convection, therefore, leads to vertical wind shear. There's another factor. So I'll talk about the natural factors first. So you have the roughness, moisture, and then the topography, of course, will lead to rising motion, and also lead to vertical wind shear, and the friction will also lead to vertical wind shear. Now, which would then lead to more differential convection distribution. Now, the effect of urbanization, I have shown about the roughness, but there is also the increase in the surface heating, which will then change the atmospheric stability and leads to rising motion. And I show a little bit about the aerosols, although we haven't shown particularly for tropical cyclones, but we think this is still a very important one because aerosols, the reason for this is that the aerosols will contribute towards a significant increase in the amount of cloud condensation nuclei, and therefore leads to the cloud droplets will go further up into become ice phase, and therefore when it comes down, you can have heavier precipitation. That's the theory that had been proposed for the aerosols contributing towards the convection. Okay, so all this will then lead to changes in the potential vorticity tendency, and leads to changes in the track. Leads to quite a few years ago, we have also studied that whenever you have these effects, then you can actually change the track, and which then change the location of the tropical cyclone landfall relative to the land. And that feeds back into these factors in here, because as the tropical cyclone shifts to a different location, that all these will contribute very differently to the rainfall. And then all these will then lead to because of this convection distribution through the tangential wind advection, it will lead to changes in the rainfall. So the basic idea is that when we have these three factors can be present whenever you have land, but then when you have the surface heating together with aerosols, you have an increased factors that could lead to more convection and therefore you will have a heavier rainfall. So I think this. So I'm just trying to highlight some of the factors that people may need to think about when they do actual prediction of rainfall. And some of these factors, for example, the roughness and then the aerosols may not be correctly represented in the models. And so therefore in your actual operational model, if these things are not included in your model prediction, in your prediction model, then it's likely that your prediction of the precipitation would be erroneous. So I think this is the last one. Yeah. So I'll stop here, and then I see that we still have 4 minutes of some discussion. So thank you very much.
Thank you very much for the interesting talk. Are there any comments or questions? Karen Maya?
Yeah, very nice, Johnny. Is it possible for you to trick the model and put in the city only insofar as it affects roughness, or only insofar as it affects the temperature at the surface? In other words, can you test in the model these factors individually? Do you plan to do that?
It might be a bit difficult if you just, well, I suppose you can do it in the model that you just increase the roughness. So we've done this in an idealized model. So the one that I show is the real thing, but we have done an idealized case in which we only increased roughness and nothing else changed. And so but for that one, we didn't look at the rainfall. We looked at the track. In fact, that was my conclusion, in that when you had changed the roughness, you actually changed the track. So in that study, we didn't look at the rainfall, but we could go back and look at the rainfall. Yeah, that's a good point. Yeah. June.
Previous some slide, yeah, maybe there for two urban or non-urban comparison, maybe. Yeah, time series.
One more.
Probably one more.
Rainfall?
Yeah, just one more talk, I think. Yeah, this one. So, I wonder, maximum wind speed, why urban is more?
Well, I think this is more on, there's no difference between the two, so it's just probably the model itself that's not doing very well in terms of simulating the intensity.
Yeah, I see.
So similarly in here, the minimum sea level pressure it's okay, but it's not good as the actual simulation, the actual observe.
So you mean that this model is good or not? You have evaluated.
The model may not be. It's not very good in simulating the intensity. Yeah, but in terms of the rainfall.
Oh, rainfall. Okay. So rainfall case.
So the rainfall it's quite good, right? So
next one maybe.
So the rainfall will show that you can actually have the two maximum as what's up. This is observed. Okay, so this is what you from the urban experiment and no urban.
Okay.
Thank you very much. Any other comments or questions?
Does aerosol itself affect the typhoon itself?
Yeah.
How it affects?
So the mechanism that's been proposed is that when you have more aerosols, you have more cloud condensation nuclei, right? And so the cloud droplets will not grow big enough until they go very high up, because there's you have more CCN to share the amount of moisture. So each cloud droplet will become smaller. So they will have to grow a lot more. So they will all go into the ice phase. When they go into ice phase, then they start to grow more. And so they become bigger before they can fall down to become rain. And so we've actually looked at a couple of cases, but we haven't finished the results, but we actually see the ice phase. If you look at the ice phase, you can actually see more meteors, hydrometeors in the ice phase than in the water phase. So that's the basic theory. And when we actually simulated that. Yeah. So that's the basic argument that why when you have a polluted air, then you can actually produce heavier rainfall because you have higher concentration of cloud condensation nuclei.
Oh, thank you.
Yeah.
Thank you very much. But interesting discussion, but we have to move on to the next. Thank you very much, Professor Johnny Chan.
Thank you.